Not floating, not planing across the surface like a speedboat skims a wake, actually suspended. Two submerged wings buried 6 feet underwater are holding 40 tons of steel, fuel, and passengers completely clear of the ocean. The boat is flying. It just hasn't left the water yet. That is not a metaphor. That is how a hydrofoil actually works. And for about 30 years, the people who built them were absolutely convinced they had invented the future of water travel. They were right about the physics. They were wrong about almost everything else. Here is what actually happened. Why hydrofoils conquered the world's fastest ferry routes and then quietly vanished from most of them, and why the reason has nothing to do with the engineering failing. To understand why the hydrofoil mattered, you first have to understand what boats are actually fighting every time they move. A conventional hull sits in the water. All of it. The entire bottom surface is in constant contact with the ocean, and every single inch of that contact creates drag. The boat is not gliding. It is bulldozing. It is shoving aside a continuous wall of water with every foot it travels. And that resistance is the fundamental reason why most ferries top out somewhere around 20 miles per hour, no matter how much power you throw at the engines. Now imagine you are dragging a dinner plate through a full bathtub. You can feel the resistance pulling back against your hand. The water piles up in front of the plate. It takes real effort just to move it a few inches. Now, lift that plate so only the very rim is touching the surface, and drag it again. The resistance nearly disappears. The plate moves easily because you have taken almost the entire surface out of contact with the water. That is what a hydrofoil does, except the plate is a 40-ton passenger ferry, and the rim is a pair of precision-engineered underwater wings, generating enough lift to raise the whole machine off the surface at speed. The wings work on the same principle as an aircraft wing. As water flows over the curved upper surface faster than it flows beneath the flat lower surface, a pressure difference builds. That difference produces lift. Enormous lift, directed straight upward through the hull above it. Below about 15 miles per hour, the foils do nothing useful. The boat sits in the water like any other ferry. Then something changes. As the engines push the boat past that threshold, the foils begin to bite. The lift builds. Slowly at first, then suddenly. The hull begins to rise. Inch by inch, the entire bottom of the boat lifts clear of the surface. The churning white water disappears. The thunderous resistance vanishes. And the boat accelerates. Hard. Because now the only things touching the water are two slender foil assemblies and their support struts. A contact area that went from hundreds of square feet to almost nothing. The drag drops by roughly 70% in the span of a few seconds. On the same engine power, the boat can now travel at 45 miles per hour across open water. That is not a modest improvement. That is a completely different category of vehicle. The Boeing Jetfoil, which ran passenger routes across the Pacific in the 1970s and 80s, carried 250 passengers on foil assemblies roughly the size of a large dining room table. Two submerged wings, each about 15 feet across, lifting the combined weight of a fully loaded city bus clear of the ocean at 45 miles per hour. The engineering was genuinely extraordinary, and it looked like the beginning of something world-changing. The Soviet Union built the Raketa-class hydrofoil starting in the 1950s and eventually operated over 400 of them across rivers and lakes stretching from Moscow to Siberia. The Italians ran Aliscafi hydrofoil services up and down the Mediterranean coast. Hong Kong used jetfoils on the route between the city and Macau, the Canary Islands, the Adriatic, the English Channel. Every major maritime nation looked at the same math and reached the same conclusion. Fast water routes, short to medium distance, high passenger demand. The hydrofoil was the obvious solution. Then the water started winning. Here is the part that breaks the whole picture, in a way nobody wanted to say out loud during the golden era. The ocean is not a clean environment. A hydrofoil foil assembly sits 6 feet underwater, moving at 45 miles per hour. That means it is hitting whatever the water contains at the equivalent of a highway impact. Floating debris, submerged logs, crab pot lines, plastic, kelp. In shallow coastal routes, the foils are operating with almost no clearance margin above the seabed. A piece of driftwood that a conventional ferry hull would barely notice becomes a structural event for a hydrofoil. The foil strikes it at speed. The loads transmit directly into the support struts and into the hull above. In serious cases, a single debris strike can bend a foil assembly enough to put the boat out of service for days. And biological fouling, the slow accumulation of barnacles, algae, and marine growth on any surface that spends time underwater, attacks hydrofoil performance in a way that is almost invisible until the numbers fall off a cliff. A fouled wing surface disrupts the smooth water flow that generates lift. The boat needs more speed to achieve foil-borne operation. It burns more fuel to get there, and eventually, it stops rising cleanly at all. Cleaning and inspecting foil assemblies means hauling the boat out of the water on a schedule that conventional ferries simply do not require. Then there is the wave problem. Rough water is not just uncomfortable for a hydrofoil. It is operationally dangerous in a specific and counterintuitive way. When the hull is up on foils in a beam sea, a large wave does not lift the whole boat the way it would a displacement hull. It hits the foils unevenly. The foil on the windward side rises out of the water and loses lift. The foil on the leeward side bites deeper and generates more lift. The boat rolls hard, faster than passengers can brace, faster than instinct can compensate. Hydrofoil routes were canceled for weather at rates that surprised even the operators who had studied the routes carefully before committing to service. The technology that made calm water crossings feel like riding a train made rough water crossings a serious management problem. All of this drove maintenance costs into a range that ferry operators had not budgeted for. Because a conventional ferry's hull is a simple, rugged shape with no moving surfaces below the waterline, a hydrofoil is a precision instrument. The foils have tolerances measured in fractions of an inch. The hydraulic systems that adjust foil angle on fully automated designs, like the Jetfoil, are sophisticated, expensive, and deeply unhappy about salt water. There is also a cost hiding inside the speed itself that most people never consider. A hydrofoil running at 45 miles per hour burns fuel at a rate that makes a conventional ferry accountant physically uncomfortable. The engines are working hard constantly, not just to maintain speed, but to maintain altitude. The foil systems require continuous power to stay foil-borne. Drop below the threshold speed, and the hull drops back into the water. The drag slams back in, and you are suddenly a very expensive conventional ferry going nowhere fast. That means a hydrofoil cannot throttle back to save fuel on a slow day the way a conventional vessel can. It is either flying or it is wallowing. There is no economical middle setting. On a route with high, predictable passenger loads, that constraint is manageable. On a route where demand fluctuates by season or day of week, running a hydrofoil at half capacity at full fuel burn is a financial catastrophe in slow motion. Ferry operators learned this the hard way across dozens of routes through the 1970s and 80s, and the lesson arrived at exactly the wrong moment. Then, in the 1980s, the high-speed Catamaran arrived. 2 narrow hulls, a wide stable deck between them, lightweight aluminum construction, and water jet propulsion. No foils, no hydraulics, no debris vulnerability. Top speed in the range of 35 to 40 miles per hour on most routes. Close enough to hydrofoil speed to satisfy most passengers. Dramatically simpler to maintain. Able to operate in sea states that would have grounded the hydrofoils sitting next to them in the harbor. The Catamaran did not beat the hydrofoil in a straight speed comparison. It won on every other number in the spreadsheet. Fuel cost per passenger mile, maintenance hours per crossing, weather cancellation rate, Useful service life before major overhaul. Route flexibility in shallow or debris-heavy water. One by one, the operators ran the numbers and reached the same conclusion the hovercraft operators had reached a decade earlier. The machine that was faster was also more expensive, more fragile, more restricted, and more dependent on conditions being cooperative. By the late 1990s, most commercial hydrofoil passenger services had been retired or replaced. The Hong Kong to Macau Jetfoil service survived longer than most, kept alive by its specific route conditions. A handful of services held on in the Mediterranean. The Soviets had already largely abandoned their river hydrofoil fleet as the economics of the post-Soviet era made operating aging vessels impossible to justify. But the hydrofoil did not disappear. It did what the hovercraft did. It retreated to the environments where its particular combination of speed and capability has no cheaper substitute. The United States Navy runs hydrofoil-derived foil systems on small patrol and interdiction vessels where